Okay. Hi, everybody. How's it going?
Good.
I'm all right. Actually, not good. I have a fat test coming up, and I spent the whole weekend grading and getting prep for that test. So I had no fun, but that's fine because, like most stuff, it gets real busy right before graduation, and then afterwards, we can all chill over the summer. And so for today's warm-up, we're going to start off with a law of sines question. We're going to get a chance to look at why the law of sines is important when it comes to solving trigonometric questions for oblique triangles. And then today we'll be doing the rest of the notes for the entire chapter. So let me start off with the warm-up. Number one, most buildings are perpendicular to the horizon. So whenever we talk about those questions where it's like, hey, your shadow is this long, a tree's shadow is this long, and you're 6 feet tall, so how tall is the tree? We can do that kind of trig because when it comes to an object standing up, we always make the assumption that the object is standing straight up, right? However, not all objects do stand straight up. For example, the Leaning Tower of Pisa, which is nearly 1,000 years old. It's like 900 years old. And over the course of its construction, they didn't have the advanced architectural techniques that we have now. And so after they started building it, part of the foundation started to give way to the soft soil underneath. And over its lifetime, it's tilted to about 10 degrees off center. So the Leaning Tower of Pisa is 184.5 feet tall. And so if you are standing on the ground looking at the top of the tower at an angle of 45 degrees, how far are you from the base? Now, the reason why we're going to have to use the law of sines in order to answer this question is the simple fact that SOHCAHTOA and the Pythagorean theorem, those rules only apply on right triangles, right? That's technically right triangle trig. And if this thing isn't standing straight up and down at 90 degrees, if instead it's 10 degrees off center, then we'll have to use our trigonometry for oblique triangles. And right now we only have half of the tools in our toolbox. We only have the law of sines. Now I'm going to warn you, this question is actually vague. You could not answer it. Why not? What could change that would affect the answer here?
How tall the person is?
Not really. Compared to 145 feet, whether or not this is a 4 foot tall or a 6 foot tall person, I wouldn't say that that will significantly impact our answer. There's a way bigger variable here.
How far away you are?
That's what you're solving for.
Maybe that's slanted, it's not straight up.
Maybe what?
It's slanted and it's not straight up.
I mean, yeah, but I'm telling you how much. It's 10 degrees off center.
Oh, wait, you don't, if you look at it from one angle, it's going to be like 80 degrees. And then if you look at it from another angle, it's going to be 100 degrees. So you don't know which angle it's tilted at.
That is the conundrum. Which side of the Leaning Tower are we on? And so what we're going to do is we're actually going to solve for both answers because we can do that. And so in case y'all didn't get that, here's the rub. What side of the tower are you on? Is it 10 degrees towards you or 10 degrees away from you? So I'm going to go ahead and draw a crappy facsimile of the Leaning Tower. So it's right here. And when I say it's 10 degrees off the vertical, that's the vertical going straight up and down. So on this side, instead of it being 90, if we're 10 degrees off, what's this angle?
80.
80. Or on this side, instead of it being 90, we're 10 degrees off in the other direction. So this side is 100 degrees. So the answer that you would get, depending on which side of the tower you're on, are you on the side that leans towards you or the side that leans away from you? That's going to change the overall answer. So on one side over here, if you are viewing the top of it at 55 degrees, how far are you from the base? So over here, I'll set up 155 degree angle. So 55 degrees. So I need you to solve for x. And then over here, if you view the top at 55 degrees, you would actually be a different height from the base. So over here, this one is 55 degrees. Let's go ahead and call that one y, the one where the tower is leaning away from you. And so based on the given information, and the other thing that you need is the height of the tower, which is why I'm giving you that here. So the height of the tower is 184.5 feet, 184.5 feet. please use this information to solve for how far a person is standing on each side of this tower. So on this side of the tower, how far would you have to stand to view the top at 55 degrees off of the ground? So from here, you look up 55 degrees. Or if it's leaning towards you, how far are you standing from the tower so that you can look up at 55 degrees at the top of the tower? Solve for both x and y, and then we'll go over this. And before we solve for x and y, depending on, before we solve for x and y for this Leaning Tower of Pisa question, I have some quick announcements. Number one announcement, chapter test is on Friday. Just because I'm giving you guys, my black pens are dying, which sucks. Like this pen is a multi-pen, so it has all these colors in it, but of course I use black the most, so you'll notice the black one is actually empty, which sucks, which is why I'm doing notes in blue. And then past that, I have my fancy green pen that I do notes with. I don't think you'll be able to see it, but the cartridge that is in it is actually tiny so that there's space for ink. And you could see on the inside how far along it is. This one is also empty. I am literally all out of black pens. I ordered a new filler for this pen because I like this one, and I'm sad that it won't be here until Friday because I wanted to do my test that I have this week in this pen. Don't mind me, I'm just being a crybaby about my lack of black ink. Nonetheless, let me put my pen back together here. You guys will have your chapter test on trigonometry Friday. We'll talk all about what that looks like on Wednesday, a little bit closer to then. And the reason why we're going to talk about what's on the chapter test Friday is that there's no class Thursday. On Thursday, I have to take my comprehensive exam to graduate. It is a test that I either pass and I graduate or I fail and I don't graduate. And that test starts at 10 a.m. and won't end until 6 p.m. So I'm basically clearing off my whole day to deal with it. I just wanted y'all to know that now. However, there's plenty of time to study and get ready for the test because today is actually our last section of notes. So tomorrow will be workshop time on this final section. Wednesday will be review and workshop time for the whole chapter. You have Thursday to study and get ready for it. And then Friday you have your chapter test. And then you won't have anything to do for me until after AP tests are all done.
Mr. Robinson, not pertaining to this specific do now, but if you get a number and you're going to round to the nearest 100, but it's like 0.004, then how do you do it? Because there's nothing in the like hundreds.
0.1, you round the 0 upwards to, wait, 0.004?
Yeah.
So it's 0.004, then it's just 0.00 because you round down on a 4. So you just don't add any value.
So it doesn't have value?
If you are rounding 1.004 to the hundredths place, this rounds to 1.00.
Up.
Because you don't round the 0 up. You leave it alone.
Yeah.
Okay. Oh yeah, so yeah, no class on Thursday. I just wanted you all to know that off the bat. The other thing is that the mid-chapter quiz is graded and up. I did that first thing on Saturday. So I uploaded the answers to the questions for your own review so that you can compare your tests to it. When I'm grading these from home, I'm grading them on my screen on Google Classroom, which takes forever. So instead of marking them up all there, otherwise I'd spend like 3 hours grading one class worth of tests, I make my grading marks on basically like the class roll sheet, like the roster. So if you would like a breakdown of your points question by question, it's not that hard for me to do for one of you. So if you guys want to know what questions you lost credit on, you can shoot me an email and I'll respond with a point breakdown of your test. But I'm not going to do that for everybody because typing all of that up for everybody would be super time consuming. Like I said, I think you can pretty easily figure out where you lost points if you compare your test to the answer key. The point values are also listed on there. So the quiz was out of 50 points total. The bonus question at the end, nobody got all of it. One person was able to get half of the answer, which I was pretty happy with. That's probably the one part of this that I do actually want to go over with everybody just because I think it's a good question. But yeah, are there any questions on the quiz? Any one of these that I can talk about or work out for you?
No.
No, y'all are all good with the quiz?
Yeah.
Okay. Yeah, the class average was pretty good, a low A, so, you know, good work hanging in there. And like I said, this trig stuff is crucial. You'll see it again next year, so if you like slack on it now, you'll regret it in the future. Anyway, let's do the warm-up, and then I wanted to show you guys the bonus question and its correct solution from the quiz, just because I think it's an elegant problem. Nonetheless, how can I approach this? So let's go ahead and solve for x first. So if you have the Leaning Tower of Pisa leaning towards you, and you view the top at a 55-degree angle, how far are you from the base of it? And just for context, you've all seen the Leaning Tower, right?
Yeah.
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 You're 61 feet, I think.
So here's the Leaning Tower, just so that we're all on the same page. Interestingly enough, the Leaning Tower used to be part of a even larger cathedral structure, because it's like in the yard of a cathedral. But it used to have associated with it an even larger building that was partially constructed and then collapsed. Weird stuff. Anyway, yeah, I heard an answer out there. So how'd you get that answer? What did you do?
I did -10, 184 divided by 100.
So number one, that doesn't work. You can't take a length and divide it by an angle. We only have one length here that we were given.
Oh.
You have the height of the tower. You have no other information. So, and this is the same like logical flow chart you should go through every time you do a trig question. Ask yourself first, number one, is this a right triangle?
No.
No, this is not a right triangle. So if it's not a right triangle, SOHCAHTOA doesn't work. The Pythagorean theorem also doesn't work. And so far in our toolbox for dealing with non-right triangles, we only have one tool. What is that one tool?
The law of sines.
All that we can actually do in this case is approach this using the law of sines, which we can do. We do have sufficient information for that. However, to use the law of sines, we need a side length and its opposite angle. And so we can see here on the right that our side length is the height of the tower this way, and 55 is its opposite angle. But if I want x, I need its opposite angle, and I don't have that, right? So what do I have to do first here?
Solve for that. Solve for the third angle, which is very easy because you already have two of the values.
Very good. I have to use the third angle theorem to get what this angle here is up top, and then after I have that, then we're up and flying with the law of sines. So third angle theorem says that this has to be what?
45.
This right here has to be 45 degrees, so that 45 and 55 is 100, 180 is 180 total. And so here is my law of sines statement. I'm going to go ahead and say that, sine A over A is going to be equal to sine B over B, where these are paired off as opposite side lengths and angles. And so we'll do sine 55 divided by 184.5. So this will be sine 55 divided by 184.5. This must be equal to sine of this angle. I don't know why the darkness dimmed again. Sine of this angle, sine of 45, then divided by that length x. And so I can go ahead and I can solve for x. In order to do that, we'll go ahead and we'll cross multiply. So this product is going to be equal to this product. So x sine 55 is equal to 184.5 sine 45. And then how do I get x alone?
Divide both sides by sine 55.
And so x must be equal to 184.5 sine 45 divided by sine 55. And so we take this and we feed it to our calculator, and we should get the answer as a decimal. So that'll be 184.5 times sine 45 divided by sine 55. And if we are on the side where the tower is leaning towards us, the side where everybody likes to take their pictures from, this one will tell us that we are standing 159.26 feet away from the base.
What if you're not standing on either side of it where it's leaning? What if you're standing like in front of it?
I actually have a good answer to that question. We will talk about that at the end.
Okay.
That's where we get into 3D geometry, and 3D geometry is a lot more complicated than what we're doing. Everything that we're doing in this class is two-dimensional. You can answer the question that you just asked with an equation, but I would have to show you the ins and outs of it, and I can tell you what kind of answer to expect.
Okay.
Yep. Okay. Item number 2, why? It's the exact same approach, but what's the difference?
It's just going to be the angle.
The angle is different, right? The setup is identical. The only difference is the angle. So on the side where the tower is leaning away from us, I'm still saying we view it at 55 degrees, but if this is 55 and this is 100, what's this angle up top?
45.
25.
Oh no, it's 25. Sorry, my bad.
This angle up top is 25 degrees. And so we'll set up the law of sines exactly the same. Here's the difference. It's still going to be sine of 55 divided by 184.5, except now this is going to be equal to sine of 25 degrees, then divided by our unknown length y. And if we take this and solve it through, we will get that y is equal to 184.5 sine 25, then divided by sine 55. It's the exact same series of inputs. The only difference is the algebra from here to here, that instead of ending up with sine 45 in the numerator, we end up with sine 25 in the numerator, which will, of course, change our answer. So that's 184.5 sine 25 divided by sine 55. And here we get that on that side of the tower, you have to stand a lot closer to it in order to view the peak at the same angle. In this case, y is equal to 95.19 feet. And again, this is all due to the fact, like these two would be the same if this tower was standing straight up and down, but because it's leaning, you're going to get a different view of it based on which side you're standing on. And so in terms of like 3D geometry-ness, right, and this is going to be a hard thing to imagine. So let's go ahead and say that like this pen here is the Leaning Tower. And the whole thing that's making it weird is the fact that it's leaning 10 degrees off center, right? So if I were to try and map this down onto a piece of paper, then I would draw a red circle for the bottom, right? I would say that this is the base of the tower. And if we're viewing it from the top and it's leaning, then the top is not going to be perfectly lined up with the base. Here we have the base, and then this blue circle would represent the top of it, right? So here's the base, blue is the top. And to show that it's leaning, they're slightly misaligned with one another. And so on one side, if you wanted to set up a, like, where would you view the top at a 55-degree angle of elevation? Well, on the side where it's leaning towards you, you are further away. You would have to stand further away. On the side where it's leaning away from you, you would have to stand slightly closer. And in these two directions out here, perpendicular to this primary difference, you would have two positions you could stand at that would both be the same distance away, because in that direction the angle doesn't matter. And this like shape that you get of like, hey, if you want to walk around while always viewing the top at 55 degrees, this would actually make an ellipse of constant viewing angle. This is way outside the scope of this class. But if you take these equations and you say, hey, I'm going to force theta to remain constant while I walk around the tower, to make that true, you would have to walk an elliptical pathway around the Leaning Tower. Are there any other questions out there about this before I move on to the bonus question?
I had a question on the do now.
Yes?
When we're solving for why for sine B, why do we use 25, angle 25?
The law of sines is dictating that you take an angle and its opposite side length and setting those to a ratio. So it's sine of 55 divided by 184.5 because they're on opposite sides of the triangle. So if you want this, you need its opposite angle. So sine of this divided by its opposite side length would give us y. The 100 and the 80, they would give us this like longer length over here on the edge. So 100 would be set to that, 80 would be set to that. And those are things we could calculate, but those aren't like real lengths. Like it would be, we tie a string to the top of the Leaning Tower of Pisa, and then we run it out here and it makes a 55-degree angle. How long is that string? There's just like nothing there, so we didn't bother calculating it. Is that okay?
Mm-hmm.
Okay. And so let me talk about the bonus question from the quiz, because I think the bonus question was spicy. And one of y'all got half of the answer, and I think the person who got it by like guess and check of the person had tried a few numbers or whatever. But let me show you guys how to solve that bonus question explicitly, because I think it's a great question. And so for the bonus, the deal is here that when it comes to solving for the altitude of a right triangle, if this is x and this is a and this is b, then we have the following special relationship. An altitude inside of a right triangle, x is equal to the square root of AB. That altitude length is the geometric mean of the two sublengths of the hypotenuse. Or equivalently, this lets us write that x squared is equal to the product AB. Both of these are the same. So in that bonus question, I was asking you to apply that logic here. And we can plug in the bits and pieces, compare and contrast, do some good algebra. And so this is telling us that this is x. The altitude here is 2 root 15, but they're not giving us the partial length. They're telling us that the total hypotenuse of the big triangle, that total thing is 16. So if I want to take this information and compare it to this formulation, this part is easy. It's going to be 2 root 15 squared is equal to what times what? So what length is this?
X.
X. And what length is this?
16 minus x. That's the part I didn't get.
That is the setup, that it is the product of this length and this length. If you do not have this amount, you have to redefine it in terms of what's given. If this whole thing adds up to 16, then 16 minus x has to give us this sublength. So this is 16 minus x. And then from here, the rest of this is algebra. Let's go ahead and see what flavor of algebra this is. 2 root 15 squared. What's 2 squared? 2 squared is 4. What's root 15 squared?
15.
So that left side is 4 times 15. And then on the right-hand side, we have to FOIL this in. So we're going to get 16x minus x squared. And now I'm going to go ahead and do some algebra. This is a quadratic equation. It has to be because this is x squared and this is linear x. And what do we always have to do to solve a quadratic?
Opposite side always has to be 0.
We need to try and rewrite that quadratic such that it is equal to 0. That's the only thing that lets us solve the quadratic equation. And so I'm going to subtract this to the other side. This is 60. So 0 is going to be equal to 16x minus x squared plus 60. And now I'm going to rewrite it in descending order as is traditional. 0 is equal to negative x squared plus 16x minus 60. And now I'm going to multiply both sides by negative 1. 0 is equal to x squared minus 16x minus 60. The reason why I want to multiply both sides by, I'm sorry, wait. I got my signs flipped. This is negative 60, this is negative 60. The reason why I want to multiply both sides by negative 1 is the fact that multiplying 0 by negative 1 still gives us 0 on the left. That doesn't change it. But typically, this is easier to look at how it factors when your x squared is positive. So now we're playing the factoring game. I need two numbers that add up to negative 16 that multiply to negative 60. Can you think of two numbers that do that?
Negative 6 and 10.
So this is equal to x minus 6 times x minus 10. Either one of these two can be 0. And so...
Wait, shouldn't it be x plus 10? Or else it wouldn't be negative when you multiply it.
So this was 60. I subtracted it over, so it became negative 60. And then I multiplied everything by -1, negative x squared, negative 16. Oh, but a negative negative becomes positive. So this is negative 60, this is positive 60, and now this is correct. A negative times a negative gives us a positive, a negative plus a negative gives us a negative. You are correct, but I made the mistake here, not here.
Okay.
Yeah, so this is telling us that x is equal to 6 or to 10. And I like this solution and think it's interesting because it seems like it's two answers. It's actually not, it's only one answer. Here's how this is only giving us one answer possible for this question. One of these lengths is going to be x. The other one is going to be 16 minus that length. So what this is telling us by saying, hey, it's 6 or it's 10, is that either, if you're getting an altitude of 2 root 15 with this relationship, it's either 6 and 10, or it's 10 and 6. Physically, it's just saying that it's either one of these answers, or you flip the triangle over and it's the same set of answers. Those are the only two numbers which will give you an altitude of 2 root 15, which also sum to 16. Are there any questions on that bonus question? It's a very fancy one. No. Okay. And so today we're going to finish notes for what we are treating as the final section of this chapter. Today we're going to finish the notes for the law of sines and the law of cosines. But before we get into that, let me do a quick flow chart for y'all in terms of like how to think about trig, and not just for the sake of this class, but on into the future. So the trigonometric flow chart. So when it comes to which solution procedure do I use when and where, we want to always try and fit that into a flowchart so that we have a recipe to follow that always gives us the correct answer. The first question that you want to ask yourself when you're asked to do trig, when you're given a triangle and somebody's asking you about the lengths and the angles going on inside of it, the first question that you should ask yourself is, well, oh my God, my brain is so dumb. I keep trying to use the black ink even though there's none left. The first thing you want to ask yourself is it a right triangle? Is it a right triangle? It's a really important question to ask right up front, because if the answer to this is yes, or if the answer to this is no, this is going to lead us down some pretty different pathways. If the answer is yes, then that tells us to open one of our toolboxes. And what are the tools in that toolbox?
For yes, it's going to be sine of cosine and sine of, oh, no, yeah. For no, it's going to be sine of law of sines, law of cosines. I can't think. And then for the yes.
Right, so if the answer to this question is yes, that means we get to do trig the way that we did in the first half of the chapter on the quiz. The world is nice and easy. We have so, ca, toa to do work with angles on. And we also have the Pythagorean theorem in case we are only being asked about side lengths for whatever reason. And of course, we know how to use these. We can use sine, cosine, and tangent both to solve for lengths or to solve for angles if we are clever enough to use their inverses. However, if it is not a right triangle, if the answer to that question is no, we then actually have to ask ourselves a follow-up question. Last week on Friday, we did the law of sines, right? And so there was one kind of scenario where the law of sines was usable. What was the rule? What do you have to have in order to use the law of sines? We built it in the warm-up. What allowed us to do the calculation?
An altitude.
No, the altitude is how we derive it. You need an opposite side and angle pair. So if the answer to this is no, we then need to ask ourselves, do we have an opposite side and angle pairing? If the answer to this question is yes, then we get to use the law of sines, which I assert is pretty easy to use. It's one step more complicated than regular old SOHCAHTOA, but it's doable. You say sine of an angle divided by a length is equal to sine of an angle divided by a length, and you cross multiply to get the piece in there that you want. Today, we are going to do our final set of notes. We're going to do our final derivation for the chapter for what happens when this question is no. If the answer to this question is no, if you do not have an opposite side and angle that are paired off, you must then use the law of cosines in order to do trig. So if you don't have a paired off opposite side and angle pair, then that funnels us into our last of these possibilities. You must start off with the law of cosines. So today we're going to wrap up our notes for this final section. This is section 6, right? Kids, is this section 6?
Yeah.
Okay.
For this section, do we have like more new chapters?
Yes.
Oh.
We have one more chapter after this, chapter 10, which is about circles.
Oh.
And then that's the last chapter.
Okay.
And so today we're going to do law of sines and cosines. Last week on Friday, we did the law of sines part just because there's a lot of notes here to deal with. Today we're going to do the law of cosines. And here's how you know that you need to use the law of cosines. The law of cosines is used to treat oblique triangles. And what's the definition of an oblique triangle, y'all?
It's not a right triangle.
Right, any triangle which is not right. So of the 3 angles, none of them are 90. The law of cosines is used to treat oblique triangles when we are provided SSS information about the triangle or SAS information about the triangle. Both of these types of data are treatable with the law of cosines. Like, you can get the answer, but you red flag in a question if they're like, hey, do this trig. If you have 3 sides or a side and angle and then another side, you must do the law of cosines to get the answer. So this is to say you're given some nasty oblique triangle and you're given A, B, C, and then you're asked about angle A, angle B, and angle C, or you are given the following information. You're given some nasty oblique triangle, but all you're given is side length B, side length A, and angle C. This is the nastiest one because look, I have this side, I don't have its angle pair. I have this side, I don't have its angle pair. I have this angle, but I don't have its side pair. If you're given 3 sides on an oblique triangle, or SAS in that order on an oblique triangle, both of these are law of cosines. The other important thing that I'd like to key y'all into when it comes to the law of cosines is that when it comes to the law of cosines, the law of cosines only has to be used once. If you're filling out a whole triangle and you use the law of cosines, you are done using the law of cosines. After that, you can switch to easier rules like the law of sines. Now, don't get me wrong. You could use the law of cosines as many times as you want in a single problem, but it has a more complicated appearance than the law of sines. And so if you want to make your work as simple and as straightforward as possible, you do the law of cosines once, you get an answer, and then after you have one of your answers, you can then switch to using the law of sines. On any given question, you should only find yourself writing out the law of cosines a single time. And so now let's go ahead and do the derivation. Let's go ahead and derive the law of cosines for ourselves to prove that it is actually a valid thing that I can write down. Now, keep in mind, and I will always make this note about derivations for those of y'all who tend to get confused. When it comes to a derivation, does that mean that this is what we are going to do every single time we saw a law, or every time we solve a law of cosines question? Is that what this means?
No, this is just kind of a start or example.
So this is why the law of cosines is a true statement. We are going to show that from first principle, but you should know that this is not how we use the law of cosines. The only thing that you are ever going to use from this is the final statement itself.
Yeah, isn't this like you're just showing us where it comes from and then like we just do the simplified statement?
Exactly. You start with the final statement, the final equation. The only reason why I make this disclaimer is that I always have people who don't understand that, who they get into the question and they start from the first line here, like they're rederiving it every time. That's not what I'm asking you to do. This is just so that we know where this comes from. And so I'm going to start off by setting up my oblique triangle over here. And inside of it, I'm placing an altitude h. And as we go around, it's going to be angle A, angle B, angle C. And so if these are our angles, what's this total side length down here?
180.
Side length.
Oh.
What is the name of this side length?
A plus B. I mean, sorry.
No, what is the name of this side length?
AB.
AB,
So
yeah,
that's the
my bad.
name of the side length. It's side length AB, but how long is it?
Okay, see.
It is side length C. What is this side length?
Side length A.
And what is this side length?
Side length B.
Keep in mind, opposite sides and angles are named with the same letter, except one is capitalized and one is lowercase. And in order to do this derivation, I'm going to say that on the left-hand side of this triangle, I have a triangle 1. On the right-hand side of this triangle, I have a triangle 2 that are each a component of this. And I'm going to call this right here on the inside, this length is going to be x. So logically, what does this length have to be?
C minus X.
On the right-hand side, this length necessarily has to be C minus X. And so what we're going to do here in order to, build out the law of cosines is we're going to do the Pythagorean theorem twice, and then we are going to get rid of X using a cosine. So first things first, let's go ahead and do some work here for triangle 1. Pythagorean theorem statement for triangle 1 would be what? Oh, I'm sorry, and this is an altitude, so this is a 90-degree angle. So what does the Pythagorean theorem look like for triangle 1?
B squared, A squared plus H squared equals B squared.
So the hypotenuse on the left is B squared. This length is H, so that's H squared. And this length is X, so that's X squared. And that's really the complete statement of the Pythagorean theorem for the left-hand triangle. Now we're going to do the same thing on the right. We are going to do the Pythagorean theorem here. And so what does the Pythagorean theorem look like for the right-hand triangle?
A squared is equal to C minus X squared plus H squared.
Yes, and here is where the interesting part of the law of cosines comes from. What is C minus X squared?
You have to foil it. You have to do a.
C
Yeah.
squared.
You have to foil it because it's telling you C minus X times C minus X. And if you do that, you're going to get C squared minus CX plus X squared, first, outer, inner, last, plus H squared at the end, that survives. So all of this becomes A squared is equal to C squared minus 2CX plus X squared plus H squared. Is that okay?
Yes.
Now, we have to keep in mind that H and X, those are not actually parts of our triangle. Those are intermediary variables. So in the end, they need to go away. So here's the first substitution that I'm going to notify you to. B squared is equal to H squared plus X squared. That's here on the left. Do you see that on the right-hand side? Do you see H squared and X squared?
Mm-hmm.
Those guys are right here. H squared plus X squared is B squared. H squared plus X squared, these guys are perfectly equal to B squared. So that's the first substitution that I'm going to make. Black pen. A squared is equal to C squared minus 2CX plus B squared. And the first thing I'm going to do is I'll rearrange this over here so that I have A squared is equal to B squared plus C squared minus 2CX. So that let me get rid of h. That's a great substitution. There's no h here now. Now all I have to do is get rid of x. And in order to get rid of x, this is where the cosine in the law of cosines comes from. What is cosine of angle A?
It's h over
Oh. No, it's going to be x over b.
Oh, I did sine.
Yeah, so cosine is adjacent over hypotenuse, so that'll be the adjacent side x, then divided by b, equals x over b. And so I can take this and I can solve it for x, where x is equal to b cosine A. And now all I have to do to get my first law of cosine statement is pop this for x in right here. And so one law of cosine statement is a squared is equal to b squared plus c squared minus 2cb cosine A. All I'm doing and going from here to here is saying that x is equal to b cosine of A. And so here I swap the x for b cosine of A. And this is one complete statement of the law of cosine. Now, please keep in mind that when it comes to this, when it comes to this, this is the equation that you use. If you're asked to do law of cosine stuff, nobody's asking you to draw an altitude or solve for x, blah, 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 blah. All of that is just a justification for why this is generally true. Now, much like how the law of sines can have three forms, right? There are different ways that we could write it. There are three different ways to write a correct law of cosines statement for your given triangle, but they all follow this exact same pattern. So notice that, and I'm just going to rewrite that last one. A squared is equal to b squared plus c squared minus 2bc cosine A. The other two versions of this follow the exact same pattern of values, and let me show you what the pattern is. This side length needs to match this angle. These two middle side lengths, B and C, need to match these middle side lengths, B and C, but the parts of it that I didn't highlight, they're always the same. It starts off with the Pythagorean theorem and then minus 2 times 2 side lengths times cosine. And so for any given triangle, this is true. Here are the other two ways that you could write this out. We could also write it in the form of b squared. We could also write it in the form of c squared, and they'll actually also be true. So if this is b, what's the angle on the other side?
B.
So on the right-hand side, this would have to be cosine of angle b. And then in the middle, what are the other two letters?
A squared and c squared.
They have to be a and c, so b squared is equal to a squared plus c squared minus 2ac cosine b. And we can also write it in the form c squared. So if this is c, what is the angle on this side?
C.
Cosine c. And if this is c, then our other two letters are a and b. So c squared is equal to a squared plus b squared minus 2ab cosine c. Any one of these three is the law of cosines, and how you should think of it is that it is a modified version of the Pythagorean theorem. So if it's a right triangle, we only care about this part. That's just the Pythagorean theorem. But if it's not a right triangle, we have to modify the Pythagorean theorem to make it correct by adding this law of cosine modifier. Only one of these three is necessary for any given question. They are all the exact same equation, but written with rotated variables.
So what do the highlighted parts represent? I don't get that.
They represent how you memorize this so that you can commit it to memory long term. The way that I memorize it is if I need to use the law of cosines on a question and I don't have access to the internet, this letter and this angle are the same. The middle stuff is the same. That way you only have to memorize the shape of it.
Oh. Okay.
So let's do one example while the iron is hot, and then I'll post the first part of your guys' law of sines and cosines homework. So let's go ahead and say that we're given that SSS scenario. We are given 3 side lengths of a triangle and asked to solve for one of the angles. So I got side length, I got side length, I got side length. And let's say that the following are our lengths. So this length here is 10. This length here is 18. And then over here on the far side, this length here is going to be 23. And what I want, and I'll just go ahead and toss the labels on here, angle A, angle B, angle C. All that we're going to do, because all we have time for today, is we want to solve for angle, pick one, A, B, or C.
B.
B.
Okay, so we're going to solve this for angle B. So the first thing that we want to do is, well, we want to check, is this a right triangle? Because if it is a right triangle, then solving for B is easy. It would have to be 90 degrees. What's the easiest way to check if this is a right triangle?
Pythagorean theorem. Pythagorean triple.
Exactly. Just set this against the Pythagorean theorem and see if it works, and it doesn't. So 23 squared versus the two short lengths squared, 10 squared and 18 squared, it doesn't add up, right? So because these two numbers are different, it doesn't satisfy the Pythagorean theorem, which is to say this is not a right triangle. So since it is not a right triangle, we then have to ask ourselves, is this the law of sines or the law of cosines? Do we have an opposite side and angle pair?
Nope.
No, we do not. And so since we don't have an opposite side and angle pair, we know we must use the law of cosines. Now, if we're looking for angle B of these three relationships, do we want equation 1, 2, or 3? And how do you know?
2, because 2 starts with B.
2 is the only one with angle B in it. So we're going to start there with that law of cosine statement, and we're just going to solve for angle B with algebra. Then and then only we can plug in our three side lengths. So I'm going to label them first. What side length is this?
A.
A.
And this one is?
C.
And this one is?
B.
Okay. And so I'm going to start off with my law of cosine statement. B squared is equal to A squared plus C squared minus 2AC cosine B. What's my first step to solve for angle B?
Plug in like B, A, and C.
No, and that's the difference between doing math when you're in elementary school and the transition to doing math when you're in college. You plug in the numbers last. We're going to solve for the variable first, and then we are going to plug in the numbers. So I want to solve for this variable, capital B. How do I get it alone?
We need to isolate it by moving it to the other side.
Okay, so what do I move first?
The cosine B?
No. I need to get this alone. So to get this alone, I need to remove this, and I also need to remove this. What do I do first?
Plus 2AC on both sides.
We're going to subtract A squared plus C squared from both sides. Now, it's important to realize that this minus 2AC is attached to the cosine with multiplication. You cannot add 2AC. That is not a valid operation. It's connected to cosine. I'm going to subtract this to the other side. So this is B squared minus the quantity of A squared plus C squared. And this is going to be equal to negative 2AC cosine B. Are there any questions on that first step? All I've done is subtracted A squared plus C squared.
So now we divide by?
Divide by what?
Negative 2AC.
Divide both sides by negative 2AC. Divide by both sides by negative 2AC. This cancels, and now cosine B is alone. So what we've just figured out is that cosine of angle B must be equal to the quantity of B squared minus A squared plus C squared, then divided by negative 2AC. And now how do I get angle B alone? How do I undo what cosine does?
You inverse it.
You invert it. So this is to say that angle B is necessarily equal to the inverse cosine of the ratio B squared minus A squared plus C squared, all then divided by negative 2AC. And so this equation is always true. This is generally true. This is a valid manipulation of the law of cosines. You can use this in other questions if you can keep track of the moving pieces. Now that we have solved it out, the rest is the act of substitution, and then we'll ask our calculator what the final deal is. So this is to say that angle B is equal to the inverse cosine of b squared, which is 23 squared, minus a squared plus c squared, 10 squared plus 18 squared, all then divided by -2 times 10 times 18, -2ac. That's going to give us our inside ratio. So this is going to be equal to the inverse cosine of 105 divided by negative -360. Yeah, 2 times 10 times 18. Wait. Yeah. Right? 2 times 10 times 18, 360.
Yeah.
And so you plug that into your calculator. What is the inverse cosine of -105 divided by 360? And we get that angle B is equal to 106.96 degrees. And that makes good sense considering that's our obtuse angle. It's opposite the biggest length, so that seems to track. Big side goes with a big angle. And now notice, in this question, I only asked you to solve for angle B. What we just found out is that if these side length markings are correct, that this angle here is 106.96 degrees, right? But if you had to solve for these other two angles, how would you do it? Now that you know that this is 106.96, how could we solve for angle A?
You could use the law of sines instead.
And then once you have two of them, how do you get the third one?
Third angle theorem.
Yeah, the third angle theorem. So when you're solving for the three angles of this type of question, number one, use the law of cosines, then use the law of sines. Then after you have two of the angles, it's as simple as the third angle theorem. Tomorrow in the warm-up, we're going to pick up from here and we'll solve for these other two angles. But for right now, are there any questions on the law of sines or the law of cosines?
Mr. Robinson, when I put that equation to my calculator, it said syntax error.
What equation?
That one, cosine -1. I mean, inverse cosine 105 divided by 360. I don't know why.
Well, it has to be negative for one. The inside of this is negative. So when you input it, it's inverse cosine -105 divided by 360, or depending on the calculator that you're using, you might have to do -105 divided by 360, hit enter, and then hit second inverse cosine, enter again, to do inverse cosine on that ratio. Also, the negative and the minus button on your calculator are different. So if you did inverse cosine of -105 divided by 360, notice this dash is a lot longer than this one. This will give you an error because minus and negative are different. On my calculator, this is negative, but the minus button is over here. If you use one when you mean to use the other, your calculator will give you issues. Anyway, I'm going to post the 8.6 homework for y'all to get started on. And then tomorrow we'll do some more examples. We'll round out the rest of this example, get its other equations, and we will also look at an example of the form where I give you side angle side information for the law of cosines. Both of those will be in tomorrow's warm-up. You all have a nice day, and I will see you tomorrow.
Bye, Mr. Robinson.
Peace.
Bye.